Hi everyone, I'm happy to share our work, TRACER, a framework for facilitating accurate and interpretable analytics for high-stakes applications. Recently, there have been growing demands of machine learning for complex high-stakes applications, such as healthcare analytics, financial investment, etc. In this work, we use healthcare analytics as our driving use case. Healthcare analytics typically refers to data analytics on selected cohort of patients for tasks like diagnosis, prognosis, etc. In recent years, neural network-based models have emerged to improve the accuracy over traditional machine learning models. An accurate analytic model can help healthcare workers and organizations to make effective decisions on patient management and resource allocation, and hence reduce healthcare costs. However, accuracy alone is not sufficient for healthcare analytics. For example, suppose we train an accurate model for in-hospital mortality prediction. We can't just report to doctors that our model predicts this patient has a 26% probability of mortality. This is unacceptable to doctors because in the life and death medical decisions, they can't just trust our model if there is no proper explanation of the prediction results. To elevate this issue, it is essential to devise a model which can derive interpretable as well as medically meaningful results. Besides, for a certain medical feature, it tends to exhibit a kind of time-invariant influence on a patient over the whole time series, reflecting this feature's characteristics. Meanwhile, this feature's influence also has some variations in different time periods or visits. Let's look at an example. We analyzed two representative lab tests, namely HbA1c and urea, for predicting patients' risk of developing acute kidney injury, AKI. We collect the medical features within 7 days. First, we train a logistic regression model by aggregating each medical feature across all 7-day data. The weight coefficient of each medical feature can be considered as the time-invariant feature importance, which reflects the influence of the features on the final prediction. Next, we train a logistic regression model over the data for each day. The learned coefficients in each day are regarded as the time-variant feature importance. As shown in this figure, we can see that different medical features have different time-invariant importance, which is validated by doctors that urea is more important for diagnosing kidney diseases. Furthermore, for each lab test, the time-variant feature importance across days varies, with minor fluctuations in HbA1c and rising importance in urea. Both the time-invariant feature importance and the time-variant feature importance are essential, but existing approaches do not differentiate them. Different from them, we highlight that it is necessary and critical to capture both time-invariant and time-variant feature importance in healthcare analytics. To achieve this goal and produce meaningful interpretation in healthcare analytics, we propose a general framework, TRACER, to facilitate accurate and interpretable clinical decision support for healthcare analytics. This is the overview of TRACER in healthcare analytics. From bottom to top, TRACER makes use of both the history time series EMR data and the daily generated EMR data, feeds such data to the core component, TITV model, which captures both time-invariant and time-variant feature importance with the collaboration of its 3 modules. Further, based on the analytic results from the TITV model, TRACER supports doctor validation with accurate and interpretable clinical decisions in scenarios including real-time prediction and alert, patient-level interpretation, and feature-level interpretation. In TRACER, a core component is the TITV model. TITV is an interpretable model which captures both time-invariant and time-variant feature importance for each sample, with the former shared across time and the latter varying across different time periods. Specifically, TITV model is composed of 3 modules: time-invariant module, time variant module and prediction module. Now let's dive into the details of each module. As for time invariant module, its aim is to model time invariant feature importance shared across time, where data in all time windows are exploited. Film, which is short for feature-wise linear modulation, is an effective conditioning mechanism that applies a feature-wise affine transformation on the input. And film is acknowledged to be good at modeling feature importance. Hence, we integrate film in time invariant module for time invariant feature importance computation. The detailed computation is shown, including the bidirectional Rn computation to capture the temporal relationship, the summary vector computation to utilize all available data in all time windows, and finally, the film generator computation for scaling parameter and shifting parameter. Next, we come to time variant module, whose aim is to differentiate the influence of different features in different time windows. Self-attention mechanism has been successfully applied for many similar tasks, so we integrate it in time variant module to compute the time variant feature importance specific to each time window. The detailed computation is illustrated in this page. With the information computed in time invariant module, we first input the time series EMR data into a revised bidirectional Rn model with film mechanism, and then employ a self-attention mechanism to derive the time variant feature importance, alpha t. Now we come to prediction module, in which we obtain the overall influence from both the time invariant and the time variant feature importance. Then compute a context vector by summarizing information at each time window. Finally, we can derive the predicted label utilizing the context vector. After introducing the architecture of our proposed TITV model, we can express the risk that a sample falls into the positive class y hat, like this. Based on this, we can derive the importance of the feature xtd to TITV's predicted label y hat in this formula. So in this case, we can re-express y hat in the form that all appearing features collaboratively contribute to TITV's final prediction. As for evaluation, we conduct experiments in both the NUH AKI dataset on hospital-acquired AKI prediction and the MIMICS-3 dataset on in-hospital mortality prediction. We compare with baselines including LR, GBDT, bidirectional recurrent neural network model, routine model, and depot model with 3 different attention mechanisms. Then we first show the prediction results. As for the interpretation results, we show both the patient-level interpretation and the feature-level interpretation, which have been validated by the doctors. Based on the prediction results, we find that TRACER outperforms LR and GBDT due to utilizing time series EMR data, and outperforms routine due to modeling the time invariant and the time variant feature importance collaboratively. Further, TRACER achieves better prediction performance than bidirectional Rn model and depot in both datasets. Besides, according to the analysis, TRACER can achieve higher interpretability than these models at the same time. We then demonstrate the patient-level interpretation results of TRACER for 2 representative patients in the NUH AKI dataset. Both patients are predicted to have a high probability of developing AKI. Some involved features are shown here. For patient 1, he may be suffering from worsening inflammation or infection, which both neutrophils and white blood cells respond to, although in different feature importance changing patterns. Then, based on the increasing feature importance pattern with time of ionized CaPOCT and sodium POCT, 2 kinds of ionized electrolytes in the human body, we presume that patient 1 is developing a worsening electrolyte imbalance, along with worsening infection, and thus at high risk of progressing to AKI soon. For patient 2, first, a relatively high and stable feature importance of white blood cell is observed, which indicates the presence of inflammation or infection. Second, the feature importance of carbon dioxide is on the increase, which is explained by the acidosis that builds up with progressive kidney dysfunction. Third, the rising feature importance changing pattern of serum sodium represents progressive sodium fluid imbalance and worsening kidney function. To sum up, such patient-level interpretation will help us understand the influential factors of a patient developing a certain disease and will hence contribute to patient management. Now let's take a look at some representative feature-level interpretation results of TRACER in the MIMIC3 dataset. Some involved features are shown here. By examining each feature importance changing patterns, we have several key findings. First, based on the patterns of serum potassium and serum sodium, we can see that low feature importance can be detected for common features, which are not generally highly related to mortality. Second, the feature importance changing patterns of temperature and mean corpuscular hemoglobin concentration justify that high feature importance can be detected for common features that are generally highly related to mortality. Third, the apparently divergent patterns of cholesterol pleural and amylase urine show that same features divergent patterns can indicate different patient clusters. More medical detailed explanations can be found in the paper. In this way, such feature-level interpretation can help us understand the characteristics of a feature in the disease development, provide medically meaningful insights, and hence contribute to the medical research advancement. Thanks for listening.